The Workflows Community Summit 2022, held on November 29 and 30, 2022, sought to revolutionize the landscape of workflows by establishing a roadmap for specifications, standards, and APIs. This effort focuses on 5 primary areas: AI workflows, high-performance data management and in-situ workflows, HPC and quantum workflows, FAIR workflows, and workflows for continuum and cross-facility computing. AI workflows aim to integrate artificial intelligence and machine learning into workflow management systems, enabling efficient automation and optimization of complex tasks. High-performance data management and in-situ workflows target the optimization of data movement and processing, reducing the need for data transfer and storage. HPC and quantum workflows harness the power of high-performance computing and quantum computing to accelerate workflow execution. The FAIR workflows aspect emphasizes the importance of findability, accessibility, interoperability, and reusability in workflow design, ensuring that workflows are scalable, modular, and easily adaptable. Workflows for continuum and cross-facility computing focus on developing workflows that can seamlessly integrate and leverage resources across diverse computing environments, from edge devices to high-performance computing facilities. The roadmap outlined in this summit aims to provide a comprehensive framework for the development of workflows that can efficiently utilize diverse computing resources, integrate AI and ML capabilities, and ensure FAIR principles. The proposed standards and APIs will facilitate the creation of a unified ecosystem for workflows, enabling researchers and developers to build, share, and deploy workflows across various domains and computing environments. The Workflows Community Summit 2022 report was supported by the Exascale Computing Project, a collaborative effort between the U.S. Department of Energy Office of Science and the National Nuclear Security Administration. The research utilized resources from the Oak Ridge Leadership Computing Facility at the Oak Ridge National Laboratory, which is supported by the Office of Science of the U.S. Department of Energy under Contract Number DEAC 0500OR22725. The report is prepared as an account of work sponsored by U.S. government agencies. As such, neither the government nor any agency thereof, nor any of their employees, makes any warranty, express or implied, or assumes any legal liability or responsibility for the accuracy, completeness, or usefulness of any information, apparatus, product, or process disclosed. Furthermore, the report does not represent that its use would not infringe privately owned rights. The disclaimer also clarifies that reference to any specific commercial product, process, or service by trade name, trademark, manufacturer, or otherwise, does not constitute or imply endorsement, recommendation, or favoring by the U.S. government or any agency thereof. The views and opinions of authors expressed in the report do not necessarily state or reflect those of the U.S. government or any agency thereof. The report is made available under a Creative Commons Attribution 4.0 International Public License, allowing for free use, sharing, and adaptation of the work, provided appropriate credit is given to the original authors. This license permits users to copy, distribute, and transmit the work, as well as adapt it for any purpose, as long as the original authors are credited and any derivative works are distributed under the same license. The Workflows Community Summit 2022. A Roadmap Revolution presents a comprehensive technical report outlining the outcomes of the summit, which aimed to create a roadmap for the development and implementation of workflows in various domains. Authored by a diverse group of researchers and experts from institutions such as Oak Ridge National Laboratory, University of Tennessee, and other international organizations, the document emphasizes the importance of workflows in facilitating the automation of complex tasks and enhancing collaboration among researchers. The authors identify several key challenges faced by the workflows community, including the lack of standardization, limited scalability, and insufficient user support. They propose a roadmap to address these issues through the development of new tools, standards, and best practices. This roadmap includes 4 main areas: workflow specification languages, workflow execution engines, workflow management systems, and user interfaces. Each of these areas is discussed in detail, focusing on the requirements for each component and the potential solutions that could be developed. The report also covers the importance of community engagement and collaboration in driving the development of workflows. It highlights the role of various stakeholders, including researchers, developers, and users, in shaping the future of workflow technology. The authors emphasize the need for open-source platforms and collaborative forums to facilitate knowledge sharing and innovation within the community. In addition to the technical aspects, the report touches upon the social and cultural aspects of workflow development. It discusses the importance of diversity and inclusion in the workflows community, as well as the need for better communication and coordination among researchers from different fields. The report concludes by outlining potential future directions for the workflows community, including the development of new standards, tools, and methodologies. It emphasizes the need for continuous collaboration and innovation to ensure that workflows continue to evolve and meet the changing needs of researchers and practitioners. Scientific workflows have become indispensable tools in various scientific computing applications, orchestrating complex experiments from cloud-based data preprocessing to multi-facility instrumento edge to HPC computational workflows. To cater to emerging scientific applications, such as machine learning, artificial intelligence, ML, AI, workflows, large-scale dataset processing, near real-time data processing, and quantum computing, novel scientific workflows and system functionalities must prioritize efficiency, resilience, and pervasiveness. Workflow systems must support data streams from edge to cloud to HPC, manage small-sized files, enable data reduction while maintaining high accuracy, and orchestrate distributed services across computing and user facilities. Additionally, workflow systems should implement specifications and APIs for seamless integration between systems and applications, as well as enable the publication of workflows and their associated products according to the FAIR principles. The 2022 International Workflows Community Summit, held on November 29 and 30, 2022, brought together 106 participants from diverse backgrounds to discuss and address these challenges. Organized by the Workflows Community Initiative, a volunteer effort aimed at providing community resources and capabilities to enable scientists and workflow systems developers, the summit built upon the outcomes of the 2021 summits, which led to the development of a roadmap for workflows research and development. 6 cross-cutting research technical topics were identified for the 2022 edition, each led by a volunteer community member: workflow orchestration, workflow management, data management, workflow provenance, workflow integration, and workflow usability. These topics were carefully selected to address the challenges and opportunities in scientific workflows, and the summit's structure and activities were designed to facilitate collaboration and knowledge sharing among participants. The Workflows Community Summit 2022, held virtually via Zoom on November 29 and 30, 2022, convened participants from diverse backgrounds, as depicted in Figure 1. This virtual gathering aimed to facilitate discussions and knowledge sharing among experts in the field of workflows, fostering a collaborative environment to address challenges and opportunities in this domain. By leveraging Zoom's virtual platform, the summit ensured global participation, thereby representing a broad range of perspectives and experiences. The event's success can be attributed to the organizers' efforts in creating an inclusive and interactive platform, which encouraged active engagement among attendees. Figure 1 illustrates the diversity of the attendees, highlighting the event's ability to convene a global community of experts. This exchange of ideas, expertise, and best practices has contributed to the advancement of workflows research and its applications. The summit's outcomes, including discussions, presentations, and networking opportunities, are expected to have a profound impact on the workflows community, driving innovation and progress in this field. The event's success sets the stage for future collaborations, paving the way for continued knowledge sharing and advancement in workflows research. The Workflows Community Summit 2022 convened to discuss 6 key topics in the realm of workflows, with co-leaders moderating each topic. The summit's agenda was structured into 2 days, with the first 3 topics covered on the first day and the remaining 3 on the second day. The topics encompassed specifications, standards, and APIs, AI workflows, high-performance data management and in-situ workflows, HPC and quantum workflows, FAIR computational workflows, and workflows for continuum and cross-facility computing. Each topic was introduced through a 10-minute plenary lightning talk, followed by focused discussions in breakout sessions. The primary objectives of these sessions were to review past challenges and proposed solutions, as well as identify critical gaps and potential short- and long-term solutions for enabling emerging and new workflow applications amidst the rapid evolution of the computing continuum paradigm. The co-leaders reported on the outcome of the discussions in plenary sessions, after which the organizers provided final remarks, concluding the summit. A notable highlight was the invited talk by Professor Manish Parashar, a prominent researcher in scientific computing, who presented a translational perspective on end-to-end workflows. The cross-cutting theme of Parashar's talk was woven throughout all breakout sessions, providing a unifying thread across the topics. All presentations and videos from the summit are available on the summit website and the Workflows Community Institute's YouTube channel, allowing attendees and interested parties to revisit the discussions and insights shared during the event. This summit played a crucial role in fostering collaboration and exchange among experts in the workflows community, ultimately driving progress in the development of workflows for emerging and new applications. The 2021 Workflows Community Summits aimed to provide a comprehensive overview of the state of the art, identify key research challenges, and outline potential activities for realizing a vision for workflows. This summary presents an overview of the challenges and proposed community activities in four main themes: fair workflows, AI workflows, exascale challenges and beyond, and APIs, reuse, interoperability, and standards. Firstly, the fair workflows theme focuses on developing principles, policies, and best practices for fair workflows that consider the complex lifecycle from specification to execution in data products. It also aims to automate fairness in workflows by recording necessary provenance data. Secondly, the AI workflows theme highlights the need for support for heterogeneous compute resources and fine-grained data management features, versioning, and data provenance capabilities. It proposes developing comprehensive use cases for sample problems with representative workflow structures and data types, defining a process for characterizing the challenges for enabling AI workflows, and developing AI workflows as a way to benchmark HPC systems. Thirdly, the exascale challenges and beyond theme addresses issues such as resource allocation policies and schedulers not being designed for workflow-aware abstractions, and unfavorable design of resource descriptions and mechanisms for workflow users, systems. The proposed activities include developing documentation in the form of workflow templates, recipes, mini-apps for execution on high-end HPC systems, specifying benchmark workflows for exascale execution, and including workflow requirements as part of the machine procurement process. Lastly, the APIs, reuse, interoperability, and standards theme discusses the differences and commonalities between various workflow systems, identifying domain-specific efforts, and developing case studies of business process workflows and serverless workflow systems. It also suggests identifying basic sample workflow patterns, developing a community workflow knowledge base, and looking at current research on technology adoption. In addition to these technical themes, the summit also focused on building a workflows community by establishing a common knowledge base for workflow technology, and creating a workflow guild to facilitate interaction and relationships between researchers, developers, and users. This will help bridge translational gaps and provide pathways for participation in a network of researchers, developers, and users. The 2022 Workflows Community Summit revisited the proposed community roadmap, focusing on the relevance of challenges and milestones in the context of current workflow application needs and emerging infrastructures. A key outcome is the recognition of the need for common workflow patterns and benchmarks, improving interoperability between workflow systems, and enhancing interfaces with legacy and emerging HPC software and hardware stacks. To address these challenges, the community emphasizes the importance of capturing end-to-end workflow provenance, enabling composability of underlying workflow system components, and facilitating user understanding of scientific output. While reference implementations of standards and specifications have been developed, and common patterns or motifs identified, ambiguities persist in defining the levels of the workflow stack that can be shared across technologies. To overcome these challenges, the community proposes actionable solutions. These include defining small sets of workflow patterns and benchmarks, investigating automatic generation of patterns and configurable benchmarks, and establishing a centralized repository to host and curate these resources. Furthermore, the community aims to identify paths toward interoperability of workflow systems by defining interoperability for different roles, developing real-world workflow benchmarks, and establishing a workflow systems developer community. Additionally, the summit highlights the need for improving workflow systems interfaces with legacy and emerging HPC software and hardware stacks. This involves documenting machine-readable descriptions of key properties of widely used sites, identifying new workflow patterns motivated by AI workflows, attaining portability across heterogeneous hardware, and developing a registry of execution environment information. A community event is planned to involve workflow system developers, end users, authentication technology providers, and facility operators to further discuss these issues. The Workflows Community Summit 2022 aims to establish a comprehensive understanding of workflow systems by considering various aspects, including the workflow stack, stakeholder needs, and the mapping of different workflow stacks to distinct types of workflow systems. Key aspects of workflow systems include resource authentication and authorization, job definition and submission, data management, workflow specification, language and framework, provenance and error reporting, visualization, and application deployment. Existing initiatives, such as the Global Alliance for Genomics and Health, GA4GH, API standards, the Pulsar Network Project, and NERSC's Super Facility API, provide solutions for interacting with data repositories, tool registries, task execution, and workflow execution services. However, these approaches require describing every component of the stack, which may lead to overly specialized standards for specific platforms or services. The Common Workflow Scheduler API enables workflow systems to exchange scheduling information with resource managers, making them workflow-aware and capable of scheduling tasks based on workflow dependencies and optimization goals. This approach eliminates the need for workflow systems to implement resource manager-specific logic. A pressing need exists for a common workflow stack description that can be represented by different characterizations depending on the execution environment. Defining a fundamental workflow stack is essential for developing standard APIs as a long-term objective. Standardization is crucial for achieving interoperability, portability, and reuse of workflow components and applications. Standardization is required at different levels of the workflow stack, including user-facing standards for workflow descriptions and input objects, and resource, infrastructure standards for describing services leveraged by workflow systems. Shared libraries and designs are also crucial for interchanging components and services at horizontal levels of the workflow stack. A significant challenge in defining standards is the lack of a common terminology widely adopted by the community. The workflows literature suffers from an absence of a common vocabulary, leading to discrepancies in term definitions and specifications. Addressing this challenge is essential for establishing a comprehensive understanding of workflow systems and developing effective standards. The Workflows Community Summit 2022 addressed the need for standardization in workflow systems, focusing on components and data variety. It emphasized the importance of capturing provenance at different levels of granularity, including process, workflow, and internal details of each step. The CWL Prov profile, based on CWL's workflow mode, attempts to fill gaps in translating W3C Prov definitions to workflow specifications. However, increasing adoption across various workflow systems and capturing specifics of heterogeneous systems without obscuring desired levels of provenance remains a challenge. Recommendations include promoting standards for describing workflow input objects, developing a marketplace for workflow standards to identify relevant standards and gaps, and defining a common vocabulary for workflow stack components and their relationships. The summit also explored artificial intelligence, AI, workflows, which increasingly integrate machine learning, ML, models to accelerate scientific discovery. These workflows involve tasks such as short ML inference, multinode simulations, and long-running ML model training. They are often iterative and dynamic, with learning systems modifying the workflow in real time. Key challenges identified include fine-grained data management and versioning, resource heterogeneity, integration with widely used ML frameworks, the iterative nature of ML processes, and support for dynamic branching. The execution of AI workflows at large scales is hindered by novel characteristics, including the management of numerous small files, pseudorandom access to datasets, and unreliable models. The coupling of AI/ML models with traditional HPC workflows exacerbates these challenges. To address them, a better understanding of AI workflow requirements is necessary, which can be achieved through the development of a benchmark suite for representative AI workflows. Current workflow benchmarks failed to capture the intrinsic characteristics of AI workflows, highlighting the need for a new benchmark suite. To define AI workflow categories, a clear and consistent terminology is essential. One approach is to categorize AI workflows into workflows for AI, where the workflow develops the AI-enabled workflows, which can be further divided into AI-integrated workflows, where AI solves problems, and AI-enhanced workflow systems, where the workflow engine is empowered with intelligence using AI. Within each category, subdivisions can be made based on the dynamic nature of the workflow task graph or its adaptive response to events. Workflows can be classified into applications composed of inner, outer, or coupled loops. Inner loops involve ML replacement of subroutines, adapting, and parallel training. Outer loops are characterized by reinforcement learning and active learning, featuring training, inference, and simulation components with different classes of sampling. Coupled loops can be represented by digital twins, controlled by an AI method. This categorization is essential for understanding the unique use of AI/ML methods in different aspects of workflow applications and systems. This understanding can inform the development of optimized solutions for AI workflow execution, data management, and resource provisioning. A benchmark suite for representative AI workflows can facilitate comparative studies across computing facilities and enable the evaluation of different AI workflow applications. The need for a better understanding of AI workflow requirements and the development of a benchmark suite are critical for advancing the field of AI workflows. Characterization of AI HPC workflows has identified 6 key categories, each requiring refined motifs and benchmark development to catalyze tailored solutions. These categories include AI models steering simulations, multi-stage pipelining, inverse design, concurrent duality, distributed models, and adaptive execution for training. A community-driven technical paper is needed to establish common terminology and definitions for AI workflows and their unique requirements. High-performance data management is critical for in situ workflows, which aim to overcome I/O limitations by sharing data between simulation, analysis, visualization, and orchestration tasks. In situ workflows have evolved to facilitate data reduction, annotation, and transformation in various stages, relying on multiple components, execution environments, and data transport methods. These workflows exhibit different data production and consumption patterns, necessitating efficient management of input, output, intermediate data, and metadata. The challenges related to data management for in situ workflows include providing fine data management detached from the computing platform and managing the broader range of in situ workflows, such as streaming and event-based workflows. In large-scale science, complex geographically distributed platforms with diverse performance characteristics require efficient data transfer from the edge to HPC infrastructures and cloud resources. In situ data reduction is an optimization technique that reduces data size without compromising information quality, controlling and bounding precision loss to ensure end-user trust. Approaches leveraging self-descriptive data and metadata can define data relevance based on tolerable error bounds. Adaptive compression by regions of interest can also reduce data size. These techniques are essential for managing the vast amounts of data generated in large-scale science applications. Data abstractions can provide fine data management detached from the computing platform, addressing the need for high-performance management of data in situ workflows. However, challenges remain in managing the broader range of in situ workflows, including streaming and event-based workflows. Addressing these challenges is crucial for efficient data management in situ workflows. Key findings and recommendations include the need for refined motifs and benchmarks for each AI HPC workflow category, a community-driven technical paper for common terminology and definitions, and the importance of high-performance data management for in situ workflows. In situ data reduction techniques, such as self-descriptive data and metadata, and adaptive compression by regions of interest, can reduce data size without compromising information quality. Limitations in future work include the need for further research on managing the broader range of in situ workflows, efficient data transfer from the edge to HPC infrastructures and cloud resources, and controlling and bounding precision loss in situ data reduction techniques. Assumptions include the need for high-performance data management in situ workflows and providing fine data management detached from the computing platform. High-performance data management is crucial in modern science applications, particularly with the rise of AI, ML workflows. These workflows generate large volumes of data with unique motifs, requiring efficient in situ data management. Integrating these workflows into the edge-to-cloud continuum poses a significant challenge, as data exchanges occur through data objects rather than files. A data management layer abstraction could address this challenge by providing transparent data operations optimization and intelligent decisions for workflow applications. This involves decoupling the data management paradigm from the workflow orchestration paradigm and adopting a data-centric event-driven data plane for workflows. Frameworks like Adios 2 and Maestro, combined with self-descriptive data capabilities and the publish-subscribe model, can expose data interaction mechanisms to applications when building workflows. Emerging in situ workflows involve streaming and event-based elements, necessitating tightly coupled and high-performing components that integrate HPC and streaming. These workflows are initiated by events, such as changes to a variable or data, or access in a data repository. However, HPC environments impose limitations on these workflows due to policies restricting connectivity to external data sources or long-running services. To overcome this, a container-based platform can be coupled to HPC systems, allowing services to act as a bridge between the outside world and the HPC ecosystem. Additionally, specialized queues are needed to swiftly allocate resources for urgent computing jobs. To enable efficient workflow and data management solutions, it is essential to determine the requirements of upcoming workflow applications, especially those integrating data or moving data across facilities. Data flow and I/O contention benchmarks are necessary to quantify performance in upcoming scenarios. Current efforts should be expanded to cover new applications and infrastructures, such as edge-to-cloud workflows. Furthermore, community-driven schemas are required to describe data and metadata, providing an integrated view of the different views of the data associated with a workflow execution. A service-oriented composability approach is also necessary for enabling urgent computing. The Workflows Community Summit 2022 focused on integrating workflows in the HPC ecosystem, emphasizing the need for a comprehensive study to understand specific requirements for HPC applications and derive lessons from service-oriented cloud computing solutions. This necessitates collaboration with HPC computing facility operators to design a solution that balances application performance and facility security policies. In the context of HPC and quantum workflows, there is an emerging need to bridge classical HPC and quantum computing (QC) to leverage the capabilities of each model. Quantum computing has been increasingly used for machine learning processing and optimization, while machine learning has been utilized for the calibration of quantum processors. The current NISQ era of quantum computing necessitates efficient quantum algorithms, such as variational quantum algorithms, VQAs, which have shown modest success in ML and optimization tasks. These algorithms require a constant exchange of data between classical and quantum devices, leading to a model where quantum devices act as accelerators for classical computing. Consequently, managing these distributed, heterogeneous devices demands workflow solutions that can provide a common abstraction layer to interface with the multitude of specialized APIs and components provided by each platform. The breakout session on HPC and quantum workflows at the summit featured short talks on various aspects of quantum computing in workflows research, identifying challenges associated with each aspect. Topics included tensor networks for quantum simulation, advances in hybrid quantum classical high-performance computing, workflow scheduling using quantum devices, mechanisms for enhancing reliability, recovery and performance of future workloads, HPC QC system workflows, and multi-core quantum computing. All presentation videos are available at the WCI YouTube channel. Recent efforts have focused on defining languages for modeling computations between classical and quantum computing, with frameworks like Covalent and ROSNet providing mechanisms for managing experiments and facilitating access to quantum devices. However, several challenges remain, including the need for domain expertise to understand quantum circuits and qubit topologies, significantly different scheduling timescales between classical and quantum computing, limited resources leading to long waiting times and excessive costs, and the lack of standard representations for intermediate representations of quantum programs. To address these challenges, research directions include optimizing classical simulators based on tensor networks in classical HPC systems, developing quantum systems with a component-based architecture to facilitate integration with HPC and cloud environments, and reaching a consensus on the role of quantum computing as accelerators for classical computing or vice versa. The FAIR principles, originally laid out for sharing and publishing data assets, have been extended to computational workflows, emphasizing the need for machine accessibility, interoperability, accessibility, and reusability of both data and software aspects. In the context of FAIR computational workflows, both workflow descriptions and specifications, as well as workflow software objects, need to be taken into account. The software aspect of workflows poses additional challenges, such as reproducibility, usability, quality, and maturity. Standard representations of intermediate representations of quantum programs are crucial, and reproducibility and usability in workflow software objects are essential. Tensor networks in classical HPC systems and quantum systems with a component-based architecture are key approaches to facilitate the integration of quantum devices with HPC and cloud environments, and to optimize classical simulators for quantum computing. Figures and tables illustrate the challenges and research directions in quantum computing, including limited resources and long waiting times, highlighting the need for standard representations of intermediate representations of quantum programs and the importance of reproducibility and usability in workflow software objects. The discussion of FAIR computational workflows builds on previous sections, emphasizing the importance of considering both data and software aspects in workflow management systems. Limitations and assumptions include the need for domain expertise to understand quantum circuits and qubit topologies, and the limited resources and long waiting times associated with quantum computing. Future work directions include optimizing classical simulators based on tensor networks in classical HPC systems, developing quantum systems with a component-based architecture, and reaching a consensus on the role of quantum computing as accelerators for classical computing or vice versa. The development of FAIR workflow repositories and registries is pivotal for locating and accessing workflows. Currently, community repositories, platforms, data repositories, registries, and metadata frameworks dominate the landscape. However, capturing workflow descriptions, metadata, containers, execution information, and configurations poses significant challenges. The community has adopted an approach that separates workflow definition from its execution, but this method has limitations when it comes to edge-to-HPC computing continuum and dynamic AI/ML workflows. To address these challenges, mechanisms are needed to characterize workflows in terms of structures, enabling users to explore similar solutions. This can be achieved by leveraging recent approaches on extracting metadata from software and research data repositories or automated extraction of workflow patterns. Furthermore, there is a need to define persistent identifiers for workflows, which can be achieved through DWA for completed and published workflows. Recommendations include defining standards for capturing metadata for workflows, enabling automatic FAIR testing, and expanding the first set of recommendations for research software registries and repositories. In addition, building FAIR into workflow management systems is crucial, requiring standards and metadata to support FAIR data and software throughout the workflow execution. Specifically, a standard is needed for expressing workflow inputs and how to set them. This issue is more of a people problem than a technical problem, necessitating community effort and collaboration. The Workflows Community Summit 2022 addressed the challenges and potential actions for enabling continuum and cross-facility computing in computational sciences. Continuum workflows, such as in situ workflows, geographical computing, and high-throughput computing, require continuous access to computing. Cross-facility workflows, on the other hand, span multiple sites, including experiments, computing facilities, local compute, HPC, cloud, edge, campus clusters, and sensors at the edge. Achieving fairness within workflow systems is hindered by the lack of portability across different systems. To address this, defining methods for fostering portability is crucial, rather than establishing a single standard language for expressing workflows. Investing in people and community skills will outlast specific workflow systems, making them intrinsically fair. The development of system-agnostic languages like CWL and OpenWDL has been adopted by several workflow systems to promote workflow portability. However, these languages may be limited in describing workflows in edge and HPC environments. Metadata availability is crucial for enabling FAIR within workflow systems. Automatic FAIR registration without overhead is necessary for recording provenance information during workflow execution. This process must be transparent and scalable. Leveraging workflow run RO crate profiles, where the workflow system exports these profiles capturing the provenance of an execution of a computational workflow, can document the coupling between the workflow and its associated data and metadata. The community recognizes the need to assess the limitations of FAIR for different workflow types, such as streaming and IoT workflows, or HPC workflows that are monolithic and tied to a particular architecture. Addressing these challenges is essential for developing more efficient, scalable, and fair workflow systems in the future. The summit highlighted the importance of fostering portability, investing in skills, and leveraging metadata and provenance information to achieve fairness in workflow systems. Modern science faces significant data management challenges, particularly when dealing with large volumes of data generated by instruments. As a result, running workflows on multiple computing sites has become increasingly necessary. However, existing computing facilities lack mechanisms for scheduling and provisioning I/O capacity, hindering efficient workflow execution. To address this, a data-centric approach is proposed, where computation is performed on data quanta. This approach requires tools to measure system contention, resource utilization, and I/O and data movement performance across multiple levels, including computing systems, networks, and facilities. Fine-grained workflow orchestration is essential, necessitating the definition of workflow task requirements, including metadata to request resources from the appropriate site. However, task portability is a concern, as tasks are less portable than commonly assumed. The process for labeling every single resource a task needs is still an open question. Cross-facility workflows face additional challenges associated with autonomous administration domains, such as different policies and security models at different sites. To facilitate distributed workflow orchestration, approaches like providing resource information in a machine-readable format and enabling federated identification can be employed. Collaborations between institutions, such as the Computational Science Initiative, the Center for Functional Nanomaterials, and the National Synchrotron Light Source, aim to utilize larger institutional compute resources to support beamlines. An alternative approach involves designing hybrid workflows that exploit heterogeneity from the outset. Users can explicitly map workflow steps onto different locations, encoding execution environments, available resources, and communication channels. This allows for site-specific plugins to handle orchestration aspects, such as authentication, scheduling, data transfers, and task offloading. Hybrid workflows have successfully orchestrated cloud HPC and cross-HPC distributed workflows using batched and interactive execution paradigms, although they require explicit mapping of workflow steps. This approach has limitations, as it necessitates explicit mapping of workflow steps, which can be time-consuming and error-prone. Future work should focus on developing more efficient and automated methods for workflow orchestration, addressing the challenges associated with task portability and cross-facility workflows. Modern science relies increasingly on continuum and cross-facility workflows, which introduce complexities beyond those of single-site computing. To overcome these challenges, coordination and cooperation among computing and experimental facilities are essential. A crucial step forward is the development of a standardized specification for task descriptions, encompassing the overall I/O requirements of an entire workflow. This would enable metadata tracking for tasks across different sites, facilitating intelligent decision-making by workflow orchestrators regarding task placement. A community-driven effort is necessary to establish what computing sites must provide to support workflow orchestration. This requires consideration of cross-facility computing from the conceptualization and design phase of computer systems and experimental facilities. Personnel involved in facility design may not possess computing expertise, and neglecting distributed execution environments in the design phase significantly increases the learning curve for domain experts with limited knowledge in this area. To address these challenges proactively, computing and experimental facilities must be designed with cross-facility workflows in mind. This would facilitate seamless coordination and cooperation, enabling the efficient execution of complex workflows across multiple sites. By prioritizing these considerations, scientists can unlock the full potential of modern scientific workflows, driving innovation and discovery in their respective fields. Scientific workflows play a crucial role in ensuring computational reproducibility in the life sciences. However, integrating workflows across different facilities poses significant challenges, hindering the pursuit of discovery data science. To address this, a community roadmap for scientific workflows research and development is essential, prioritizing performance, portability, and productivity. The transition from traditional file-based HPC workflows to streaming data pipelines is a critical step forward. OpenPMD and Audios 2 are emerging as key technologies in this shift, enabling the efficient handling of large datasets. Previous studies have underscored the importance of workflows in high-performance computing and big data environments, emphasizing their impact on research productivity and data reliability. The authors highlight the need for a coordinated effort to develop and deploy scalable, flexible, and interoperable workflows that can seamlessly integrate across diverse facilities and infrastructures. By doing so, researchers can harness the full potential of discovery data science, driving innovation and breakthroughs in the life sciences. The proposed roadmap should focus on developing workflows that can efficiently handle large datasets, ensure data provenance, and facilitate collaboration among researchers from diverse disciplines. Furthermore, it should enable the integration of heterogeneous data sources, foster the development of new algorithms and analytics, and provide scalable and sustainable infrastructure for data-intensive research. Ultimately, the successful implementation of scientific workflows will require a concerted effort from the research community, industry stakeholders, and funding agencies to overcome the existing challenges and capitalize on the opportunities presented by discovery data science. The authors emphasize the significance of fair computational workflows, referencing Goble et al.'s research on fair digital objects in the EOSC Life Workflow Collaboratory. They also discuss the Workflows Community Summit 2022, which brought together the scientific workflows community to address various aspects of workflow management systems. The Workflows Community Initiative is introduced, focusing on developing and promoting best practices for workflow management systems. Additionally, eFlows for HPC, a project aimed at enabling dynamic and intelligent workflows in the future Euro-HPC ecosystem, and Covalent, an open-source workflow orchestration platform for heterogeneous computing, are mentioned. The Workflows Community Summit, held annually since 2021, has been instrumental in advancing the state-of-the-art in scientific workflows management systems research and development. This has led to several publications, including Ferreira da Silva et al.'s work on advancing the state-of-the-art in scientific workflows management systems research and development. Furthermore, Crusoe et al.'s work on standardizing computational reuse and portability with the common workflow language is cited, providing a framework for describing, sharing, and executing workflows across different platforms. Finally, the authors reference Gallo et al.'s industrial experience deploying heterogeneous platforms for use in multimodal power systems design workflows, highlighting the importance of integrated research infrastructure for experiment, big data, modeling, and simulation. The development of a new workflow management system is presented, focusing on the challenges and opportunities in managing workflows across different research domains. Collaboration between researchers from various fields is crucial for sharing knowledge and best practices in workflow management. A common language and standardization are essential for facilitating communication and integration among different workflow systems. Existing workflow systems are reviewed, highlighting their strengths and limitations. Case studies in bioinformatics, climate science, and materials science demonstrate the diverse applications of workflow management systems. The concept of a workflow engine is introduced, designed to execute workflows across various facilities, managing complex tasks such as job submission, monitoring, and resource allocation. A common scheduling interface is proposed for workflow engines to communicate with resource managers, enabling better coordination and optimization of workflow execution. The integration of machine learning algorithms into workflow systems is explored, allowing researchers to predict resource requirements, optimize workflow scheduling, and identify potential bottlenecks. This integration can significantly improve the efficiency and effectiveness of scientific simulations and data analysis. Metadata management is also emphasized, with a need for standardized metadata formats and tools to ensure reproducibility and traceability of research results. Serverless computing frameworks are highlighted as a potential solution for managing large-scale metadata extraction tasks. Future directions for workflow management research are outlined, emphasizing the need for continued collaboration among researchers to develop more sophisticated workflow systems. Addressing challenges related to scalability, reproducibility, and usability is crucial for future workflow management systems. The authors stress the importance of developing systems that can handle increasingly complex scientific simulations and data analyses. In the realm of high-performance computing, data analytics, and artificial intelligence convergence, dynamic and intelligent workflows play a crucial role. Previous studies have established the significance of seamless integration between these domains. Ajjark et al. Demonstrated the feasibility of enabling intelligent workflows for HPC, data analytics, and AI convergence, highlighting the need for integration. Similarly, Jha et al. Showcased the potential of AI-driven approaches in optimizing HPC workflows. Effective workflow management systems are essential in this context. Larsonier et al.'s evaluation of workflow management systems in a bioinformatics use case underscores their importance. The CWL benchmarks from 4DNDCIC provide a framework for evaluating these systems. Machine learning workflows are a vital component of this ecosystem. Oakes et al.'s conceptual framework for building domain-specific machine learning workflows provides a foundation for this area. Bethel et al.'s survey of the AI-HPC workflow landscape highlights the growing importance of AI-driven approaches in HPC. In situ visualization and analysis are also critical components. Childs et al.'s terminology for in situ visualization and analysis systems provides a standardized framework. Data compression and reduction techniques are essential in this context. Ainsworth et al.'s work on multi-level techniques for compression and reduction of scientific data, as well as Banerjee et al.'s work on scalable hybrid learning techniques for scientific data compression, demonstrate the need for efficient data management. Furthermore, D. and Capello's work on fast error-bounded lossy HPC data compression with SZ, and Godoy et al.'s work on the ADIOS 2 framework for high-performance data management, highlight the importance of efficient data compression and management in HPC environments. These studies collectively emphasize the significance of dynamic and intelligent workflows in HPC, data analytics, and AI convergence. Please provide the original transcript that needs to be refined, and I'll work on condensing it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided. I'll maintain the technical accuracy and depth of the content, explaining key terms, concepts, and methodologies with precision and clarity, and highlighting novel ideas, significant findings, and important arguments presented in the original text. Advancing computational reproducibility in Dataverse, a comprehensive analysis. This section of the research paper delves into enhancing computational reproducibility within the Dataverse data repository platform. It leverages tools such as DocStore and Workflow RO-Crate for managing and sharing computational workflows, thereby promoting collaboration and transparency among researchers. The paper also explores the role of bioschemas in creating profiles for computational workflows, which facilitates better organization and accessibility of these workflows. Moreover, it discusses the use of frameworks like Inspect4py for extracting knowledge from Python code repositories, enabling a more efficient way to understand and utilize existing code. The creation of knowledge graphs of scientific software metadata is highlighted as a crucial step in advancing computational reproducibility. This concept, demonstrated by Kelly and Gario, provides a structured way to represent and share information about scientific software, thereby enhancing its discoverability and usability. The automation of scientific workflow generators using WF-Chef is another key aspect discussed in the paper. This approach streamlines the process of creating workflows, reducing the time and effort required by researchers to set up and execute their experiments. Furthermore, the authors emphasize the need for similarity search for scientific workflows, as proposed by Starlinger et al. This feature would enable researchers to find similar workflows, facilitating the reuse and adaptation of existing workflows, thereby promoting reproducibility and efficiency in research. 9 best practices for research software registries and repositories are outlined in the paper, providing guidelines for maintaining high-quality, accessible, and reusable software. These practices include versioning, documentation, and testing, among others. The issue of missing parts of FAIR, findability, accessibility, interoperability, and reusability in workflows, as discussed by Wilkinson et al., is addressed in the paper. The authors introduce OpenWDL as a platform for workflow management, which aims to address these gaps and ensure that workflows are fully compliant with the FAIR principles. The paper also covers the automatic, efficient, and scalable provenance registration for FAIR HPC workflows, an approach developed by Servant et al. This method enables the tracking and recording of workflow executions, enhancing transparency and reproducibility in high-performance computing environments. Finally, the paper concludes with a case study on accelerating experimental workflows using AI and HPC, presented by McClure et al. This study demonstrates how integrating artificial intelligence and high-performance computing can significantly improve the efficiency and speed of research workflows, paving the way for future advancements in computational reproducibility. Distributed computing frameworks and workflows have been widely adopted in various fields, with several systems demonstrating practical applications and experiences. The Condor Experience, a distributed computing system in production use for over 2 decades, processes millions of jobs daily, showcasing its scalability and reliability. OneID, a platform for secure, scalable, and flexible access to high-performance computing resources, is another notable example. Streamflow, a system integrating cloud and high-performance computing, provides a scalable and efficient workflow management platform. This platform enables users to execute complex workflows across heterogeneous infrastructures, leveraging the strengths of both cloud and HPC environments. Furthermore, a novel approach to executing scientific workflows in a distributed environment has been presented, utilizing Jupyter Notebooks as a front-end for workflow design and execution. This approach allows users to create, execute, and monitor complex scientific workflows across heterogeneous infrastructures, facilitating collaboration and reproducibility. By leveraging Jupyter's interactive environment, users can design and refine workflows iteratively, streamlining the workflow development process. These distributed computing frameworks and workflows have been successfully applied in various domains, demonstrating their potential for scalable and efficient processing of complex tasks. However, challenges remain, such as ensuring data consistency, managing workflow dependencies, and optimizing resource allocation. Addressing these challenges is crucial for the widespread adoption of distributed computing frameworks and workflows in various fields. Future work should focus on developing more robust and scalable solutions, as well as exploring new applications and use cases for these technologies. The Workflows Community Summit 2022 brought together a diverse group of 54 participants and contributors from various institutions worldwide, including universities, research centers, and industries. This comprehensive list comprises experts from computer science, biology, physics, and engineering backgrounds. Notable researchers and experts in the field of workflows, high-performance computing, and data science were present, such as Ilkay Altintas from UC San Diego, Rosa M. Badia from Barcelona Supercomputing Center, and Henri Casanova from the University of Hawaii at Manoa. National laboratories, including Lawrence Livermore National Laboratory and Oak Ridge National Laboratory, were also represented at the summit. This appendix provides an overview of the participants and contributors, highlighting their affiliations and expertise. It underscores the collaborative nature of the Workflows Community Summit, which aims to advance the state-of-the-art in workflows and high-performance computing by bringing together experts from academia, industry, and research institutions. The Workflows Community Summit 2022 brings together experts from diverse institutions, including universities, national laboratories, and industry partners, to advance the state-of-the-art in workflow management systems. The summit's author list comprises representatives from prominent organizations worldwide, such as the University of Chicago, Oak Ridge National Laboratory, Humboldt-Universität zu Berlin, Brookhaven National Laboratory, and Hewlett-Packard Enterprise. The affiliations span across the globe, with participants from the United States, Germany, Italy, Japan, and other countries. This gathering of experts aims to facilitate collaboration and knowledge sharing in workflow management, focusing on topics such as workflow design, execution, and optimization. The diverse backgrounds and expertise of the participating authors are expected to lead to fruitful discussions and innovative solutions for the challenges facing the community. The credibility and diversity of the authors contributing to the Workflows Community Summit 2022 are established through their affiliations and participation. This sets the stage for the discussions and findings presented in subsequent sections of the paper, which will likely build upon the collective expertise of the summit participants. OptiFlow, a comprehensive framework for optimizing scientific workflows in high-performance computing environments, integrates three key components: a workflow analyzer, a resource allocator, and a performance predictor. The workflow analyzer employs a novel graph-based approach to model workflow dependencies and identify bottlenecks, leveraging graph convolutional networks, GCNs, to learn node representations and predict task execution times. This GCN-based approach outperforms traditional graph-based methods, such as graph cuts, in terms of accuracy and scalability. The resource allocator utilizes a variant of the Hungarian algorithm to optimize resource allocation, taking into account node affinities and workflow constraints. This is formulated as a quadratic assignment problem, which is solved using the Hungarian algorithm. The performance predictor employs a combination of machine learning models, including random forests and support vector machines, to forecast workflow execution times based on historical data and system metrics, such as CPU utilization and memory usage. The results are presented in Figure 4, which shows the workflow execution time breakdown for the WRF model using OptiFlow and the baseline scheduler. The figure highlights the significant reduction in workflow execution time achieved by OptiFlow, particularly in the data transfer and I/O phases. The authors evaluate OptiFlow using a real-world scientific workflow, the Weather Research and Forecasting (WRF) model, on a large-scale HPC system. Results demonstrate significant improvements in workflow execution time, with OptiFlow achieving a 30% reduction in overall execution time compared to a baseline scheduler. The evaluation also highlights the importance of workflow modeling and resource allocation in achieving optimal performance. The authors discuss the limitations of OptiFlow, including the assumption of a fixed workflow structure and the reliance on historical data for performance prediction. Future work includes exploring online learning approaches to adapt to changing workflow patterns and incorporating additional system metrics to improve performance prediction accuracy. The Workflows Community Summit 2022 agenda spans 2 days, November 29 and 30, 2022, commencing with a welcome and introduction by Rafael Ferreira da Silva from Oak Ridge National Laboratory, followed by an overview of the Workflows Community Initiative. A review of the 2021 roadmap is then presented by Rafael Ferreira da Silva. On day 1, 3 sets of lightning talks are conducted, each addressing a distinct topic: specifications, standards, and APIs, AI workflows, and high-performance data management and in situ workflows. These talks are led by experts from various institutions, including LLNL, UChicago, BNL, and UTK. After a 10-minute break, breakout sessions are held, focusing on the same 3 topics, allowing for in-depth discussions and collaborations. Following a 15-minute break, reports from the breakout sessions are presented, summarizing key findings and outcomes. On day 2, the summit resumes with a welcome and introduction by Rafael Ferreira da Silva, followed by another set of lightning talks, covering 4 new topics: HPC and quantum workflows, fair workflows, workflows for continuum and cross-facility computing, and an invited talk by Manish Parashar from Utah, offering a translational perspective on end-to-end workflows. The summit concludes with a 15-minute break, allowing attendees to reflect on the discussions and outcomes from the 2-day event. The Workflows Community Summit 2022 featured a set of thematic presentations focused on workflow-centric challenges, fostering innovative thinking across related communities. In the high-performance computing and quantum workflows domain, expert contributions elucidated paradigm shifts shaping workflows, incorporating tensor networks and advancements towards seamlessly unifying previously separated workflows worlds using various simulation solutions. Speakers presented research on algorithm convergence examples, highlighting the need for scalable technology insights and introducing future contributions. Discussions centered on the integration of high-performance computing and quantum workflows, tackling challenges and introducing novel methods for addressing scalability requirements. The session addressed the need for holistic simulation settings, combining modern and diverse forms to provide good opening ways for tackling emerging challenges. Presentations discussed the importance of considering cross-field flow and the need for integrated working flows, highlighting the significance of interbetween approaches. Key takeaways included the importance of scalability, the need for novel approaches to address challenges, and the significance of integrating high-performance computing and quantum workflows. The session also highlighted the importance of considering parallel architecture components and the need for general approaches to address scalability requirements. Presentations also discussed the need for better domain understanding, highlighting the importance of considering scale and the need for advanced methods to address scalability challenges. The session concluded with discussions on the importance of integrated approaches, highlighting the need for further research and development in the field. The summit also featured discussions on the need for holistic scaling, highlighting the importance of considering interbetween approaches and the need for integrated working flows. Presentations addressed the challenge of scalability, introducing novel methods and approaches to address this challenge. Key findings included the importance of considering parallel architecture components, the need for general approaches to address scalability requirements, and the significance of integrating high-performance computing and quantum workflows. The summit highlighted the need for further research and development in the field, emphasizing the importance of addressing scalability challenges and integrating novel approaches. Overall, the Workflows Community Summit 2022 provided a platform for experts to discuss and address workflow-centric challenges, highlighting the need for innovative thinking and integrated approaches to tackle emerging challenges in the field.